Today's Bob P. Show is sponsored by National Instruments. National Instruments is a technology pioneer and leader in virtual instrumentation, a revolutionary concept that has changed the way engineers and scientists in industry, government, and academia approach measurement and automation. Leveraging the PC and its related technologies, virtual instrumentation increases productivity and lowers costs through easy-to-integrate software, such as the LabVIEW graphical development environment and Signal Express interactive measurement software, and modular hardware such as PXI modules for data acquisition, instrument control, and machine vision. Together, National Instruments measurement software and hardware products provide today's engineers with an integrated test platform to accelerate their product development cycle and achieve a faster time to market. National Instruments.
Almost live from National Semiconductor, the analog IC design and manufacturing capital of the world, it's the Bob P. Show. Here's your host, Bob Pease.
What? Oh, this distortion stuff. Anyhow.
Okay.
With Bob Pease and also with Paul Rako.
That's me. How you doing, Bob?
And with Paul Grohe. I like your other version better, but that's okay.
That's
and
all right.
with Clay Daigle from National Instruments. And Paul will explain what Clay Daigle from National Instruments is going to talk about.
Oh, he's going to talk about groovy stuff. That's the magic word, as Frank Zappa would say. Groovy. Andy Aronson's got us on groovy today. So the groovy thing we're going to do is we've got Clay Daigle. He's a staff engineer at National Instruments. Not to be confused with National Semiconductor, that's us. National Instruments is down in Austin, Texas. For the past 5 years, Clay has been designing front-end instrumentation amps. Real tough job, so he knows what he's doing. And he works for NI Data Acquisition Products. They do a lot of stuff, software, they're world leaders in what they do. And he works on low-powered instrumentation amps for bus-powered applications. He got a BSEE in electrical engineering from Texas A&M University. And I'd like to know what the A and the M stands for. Clay, come on down.
Mechanical.
Do you know?
I know.
Oh,
All right.
Hi, come on in.
hi.
Come on in. Pleasure to have you here.
Hi, nice,
Pull up
nice
a
to meet
chair
you guys.
here. We
Thanks
got
for,
some slides.
thank you for having us. The A&M, it doesn't stand for anything anymore, actually. It
Really?
used to stand for agriculture mechanical. Now it's just
A&M. Okay. Well, that's good to
Okay.
know.
So one question answered. One
All right. That's done.
Okay, now I'm going to explain about this general purpose distortion stuff, such as the fact that all amplifiers distort. Even the ones that don't distort very much distort a little bit, and if you go faster and faster, they get usually worse and worse. Now we're going to bring up a few examples today. LM324, which is a high distortion amplifier, and the LM324, which can also be a low distortion amplifier. We'll explain that later.
That kind of contradicts
I
things,
think,
Bob.
well, that's the whole
How can
point.
it be both at once?
We have to change one thing.
Rod Serling's going to come
We
out of
have
the
an
closet
LF412 type. We have
LF, right?
LF412,
Yeah,
old-fashioned
JFET.
JFET input. And we're going to talk about LMV324. We may not get the distortion, I can't even spell distortion, but we'll fix that. Not a big problem today.
Distortion,
And
analog
we're going to
power
mention
point.
the LMH6722, which is
Yeah.
very fast with also very low distortion.
And that 7 is a current feedback amp.
That current
66
7
are
is a
voltage
very
feedback,
fast,
67
yeah.
are
How
current
is
feedback.
distortion defined? Well, we often say it's percent of signal. In other words, under specified conditions, this amplifier has 0.01% of signal. But under different signal sizes, it's undefined. dB, again, under controlled and specified conditions. What kind of distortion do we have? Well, there's crossover distortion. Some op amps that we'll discuss today have mediocre, lousy crossover distortion. You can have slew rate. You could have slew rate that's asymmetrical. We could have loss of gain on one side where the gain just poops out because the transistors don't have enough gain. You could have loss of gain near clipping. You could have oscillation up near clipping.
The fuzzies.
Oh, yeah.
All right.
You could have square law distortion, such as you get from vacuum tube amplifiers that a lot of people like because they're Class A, low distortion square law amplifiers with vacuum tubes only 1% distortion.
That's how the load line plays with
Yeah.
the characteristic curves of the tube.
Yeah.
That's
now,
in the square line.
Here's some views. I like to work in crossplot. So you crossplot the input and the output. Well, this is maybe a little distorted, but Class A amplifiers typically do distort up or down on both ends.
Ideal is 45 degrees, right?
Let's say the gain, perfect gain would be linear.
Every volt you get on the input, you get the exact same volt.
Or
so
at least proportional.
And as it goes, the sine wave, it rattles back and forth
Yeah.
on that 45 degree.
Or it could be just bent because it doesn't have enough gain on one side. Or it could have crossover distortion. Every time it crosses over, it has a lump. Now, what other kinds of things do we have to do? We have to measure it. Well, you put a low distortion sine wave in, you measure the output. You measure here, but you also really need to measure here, because if the input is distorted and the output's the same, you can't get mad at the amplifier.
Right.
And we'll discuss that in 1 minute.
Paul has some tricks for cleaning up the input, right?
Now, here's what I like to do is you put in a fairly low distortion sine wave and you subtract the output from the input with equal resistors.
Cool. Inverting amplifier, so it's just
Inverting
minus one,
amplifier,
right?
Yep, so it's gain of -1. A lot of op amps are used and characterized at -1. And you subtract it. Now, you don't need to use an op amp here, but an op amp is okay because these signals are very small and this is very well behaved. And you can measure here. And now you don't have to say, well, I've got 1 millivolt of error in a 12 volt signal. You can say, I've got 1 millivolt of error in a 1 millivolt signal.
And this is just trying to keep the voltage divider from being unloaded? You're trying to buffer
Yeah, if you could look here and not look
and not
here.
draw current out of it,
But
which would
if you had
affect
a scope that's 20 picofarads, pretty soon you're going to get screwed up. So it's better in general to use a little op amp to buffer it. You could use a follower buffer. Now, I would call this subtracting mode, and the subtracting mode could be inexpensive. It could offer you good resolution, but the reason I like it is you get good insights because you can see where the problem is. Is the problem on this end or this end? Is the problem in the middle?
Where on the waveform things are going wrong?
Yeah, because a real direct reading distortion meter will just say, it's distorting somewhere and this is how much there is. I like to see where it's happening.
The guy like you that knows how the inside of an op amp works can maybe get some hints about what's going wrong inside the op, what stage is screwing up by seeing where in the waveform things are going wrong.
Now, if you want to take direct measurements of the distortion, it may take an expensive machine. We'll discuss that in a few seconds. Especially at high frequencies, it may take a lot of bucks, but not necessarily. But I still like to use the subtracting machine because it gives me good insights. Now, direct measurement of distortion is not necessarily too expensive, and we'll discuss that. Now, here's an example. We'll take an example of the good old LM324 that was designed to be a pretty good general purpose amplifier, but low power and not low distortion. So you put this into an amplifier situation. You ask the op amp to invert, and it is not a low distortion amplifier. Because when this has to jump a volt or a volt and a half all of a sudden, it can't do it. At 1 hertz, it's not bad for distortion. At 1 kilohertz, the word is awful.
This is the output stage?
This is the output stage.
Okay.
This is a
And then this is just all the front end, the diff pair. You've just made a triangle to show
simplified
all
version
that.
of the LM324. Now, we make a lot of it. In fact, this is the worst amplifier we make for distortion. We couldn't improve it. People would hate it. Now, to make this amplifier work well, all you have to add is a pull-down resistor to the minus rail. And now this is, yes, a low distortion amplifier.
Is that in the data sheet for the 320? It is in the 358, right?
Well, the 358, the LF or the LMV 358 doesn't need the pull-down resistance.
Yeah, it's a new part. It's
It was
beauty.
designed not to do that.
Right. But the old LM 358 has a note in the data sheet because
Actually, I do. It's more folklore, and I think in an app note, but it doesn't say in the data sheet itself.
Well, we're going to prove it today. We will show you that
cool.
the distortion will improve.
When you load that, when you pull it out of Class
load
AB
that.
mode, yeah.
Now, there are other op amps that really don't like to oscillate without a pull down for audio work. LM709 will work okay at a megahertz, but not okay without a pull down. LM10 is similar. The LM10 is a wonderful amplifier. We discussed it a few weeks ago.
Yeah.
But without a pull down, it's kind of mediocre or lousy. Now, I showed you before the nominal circuit I use with R and R. I like to use 21K. Why? Why 21K? We were running low on 20K, so I said, I won't use up our last 20Ks. I'll use 21K, 5 places, and I'll make an inverter. And I threw in a 1K with a 10,000 picofarad filter. Now, to see low distortion at 20 kilohertz, Paul, would you have a comment on what kind of bucks it takes to see low distortion at 20 kilohertz?
Oh, you can buy used equipment, some HP equipment, some audio precision equipment for the $500 to $1,000 range. But to really get the good equipment, it's probably going to cost about $2,000 to $5,000 to measure in that range.
In the audio frequency band.
In the 20 hertz to 20 kilohertz range.
Something that we trust to put on a data sheet.
Yes. And normally when we do this kind of measurement, we like to use standard equipment that everybody uses, industry standard equipment. So if somebody comes back and questions us, how'd you do this data sheet curve? We use the AP1 and we set it up this way.
Use the NIDSA.
Exactly.
44,
You didn't have that around when we were doing
But
this.
we will be using it from now
We may
on.
be using it a lot. Now, when you push up the bandwidth to 60 megahertz, what kind of bucks is it going to take?
You get into more bucks because the analyzer required is much more expensive. You have to use an RF spectrum analyzer, which right off the back that can be $5,000 to $10,000 to $15,000, depending on its noise floor and how well it can handle input overload and how well it can handle what its dynamic range is. The better analyzer is going to be more expensive. So the base analyzer, the one we use, is about $15,000.
Wow.
And that's just for the analyzer.
Now, if it's at 60 megahertz you're measuring, what's the bandwidth of the analyzer? Do you get a 200 megahertz analyzer?
Well, just whatever up to the harmonics you need. So if you're measuring 60 megahertz, you need to be able to measure 12 and 18 or 120
and go all the way
megahertz,
out, right?
180
So
megahertz.
you don't need a 60 megahertz spectrum.
But you need to be able to look at the fundamental, and then the second, and the third, and the fourth, and the fifth.
Yeah, most of it's up to 5. Is that generally true?
It's usually the second and third, but just for fun, we like to measure
We're
out
cool,
this
though.
and see.
You do the good stuff. So
Okay, now we're going to mention this fella, or we'll duck it.
we're going to go over to the lab now. Do you want to do that?
Well, we're going to do this before we go to the lab, right?
Okay, so
Let me
do
move
that,
out of the way.
and then we'll talk about the nice Penton people.
What I want to do is go a slightly different direction, and I'm just going to borrow your space here.
Absolutely.
Now, a problem that we face sometimes isn't that we can't go fast enough, or it's not that we're measuring 60 megahertz. A problem that you can have sometimes is too much delay. So let's say that this little cloudy thing is a stereo from Bose maybe, or something like that, where we want to measure its output distortion. Now, the problem we have is that the delay through this circuit doesn't really let you do the analog subtraction method. So you're going to have to capture the entire signal on the output, and you're not going to be able to do the little trick. So
Yeah, like they're running it through a surround sound processor. So
right,
there's
right.
going to be
So
a delay.
So this is the method. This is the method that we hinted at earlier, where you do the subtraction. And the problem that you're going to have is you'll have your input sine wave, but your output sine wave may be shifted by a lot. And when you subtract them, you're still stuck with a sine wave. So you haven't gotten anywhere. So what I'm going to talk about is a way that National Instruments has to view this signal. And the tools we're going to be using are the NI 4461 and also some software that we have called Signal Express.
Okay. Is this a 4461
This is a 4461. This is an audio range. It's a dynamic signal analyzer. It has 2 analog outputs and 2 analog inputs. So this is represented by this little box. We're going to output a sine tone on its analog output. It's going to go through our delay, our circuit under test, which is just represented as an inverting amplifier right now, but it could be anything. And then we're going to read the signal back, and we're going to analyze that signal. Now, one of the drawbacks that Bob mentioned was that whenever you do this type of analysis, with a typical distortion analyzer, you don't know what the distortion looks like. You don't know if it's crossover distortion. Right. You don't know if it's slew rate limited. You don't know if it's rounding at the endpoints. You don't know. And as a design engineer, you need to know because you're trying to fix it. You're
make it better at least.
You're trying to make it better. So what we do at National Instruments, we allow you to capture this entire signal, and then the 4461 has enough dynamic range that you can perform this subtraction in software. And we'll do that subtraction in National Instruments, I forgot the name of our software.
Signal Express.
National Instruments.
It's the great stuff. This stuff, we were raving about it because we, when you guys showed it to us, Paul was saying, "Oh my God, this stuff." I mean, you guys invented like LabVIEW, and that's the world standard.
Or
But
have
it-
Windows.
Yeah, it's a heavy lifting kind of program. It's something for a test group to set up and do this huge test, where Signal Express to go bang, bang, and do what we're going to do here. It's
Signal
awesome.
Express is built on LabVIEW. At its heart, we used LabVIEW in order to create parts of Signal Express. So a lot of the power that's in LabVIEW is in Signal Express, but you don't have to be a programmer to use it. It's a tool that an engineer who's not a programmer, not familiar with writing code,
hardware guys
it's
like
hardware
us.
guys.
Yeah, us
you can
kinda
go
guys.
in, you can play with it on the fly, you can change settings, you can do all this stuff. All the details are taken care of for you, all the programming, setting up the instruments, all that. You don't really have to worry about that. That's taken care of, and you basically can have fun doing your job. You can look at the distortion the way you want to.
Yeah, because I remember whenever I saw a VXI Bucks, I just shuddered to think of all the C code that would have to be written and all the debugging that would have to go on. And what you showed me was a lot easier than
We're
how I
gonna
remember
get to
using
show everybody.
Raspberry.
Yeah, just put it in and get it working. So lab sponsors.
Lab sponsor.
Penton Media. They publish Electronic Design Magazine. Great magazine.
Good,
Bob
good.
Pease writes in it. Electronic Design is a trusted information source for design engineers and engineering managers, delivering the latest news on key technologies, design, product, and professional information. Electronic Design readers stay up to date on all important aspects of engineering that impact design and technologies, while offering competitive product advantages, including issues surrounding professional, legal, career, and management matters.
Very good.
Bob Milne?
Yeah, Milne. Yeah.
He works there, huh?
Yes.
He's
He's
a
one of
great
my lead editors. Now, shall we go over to the bench and look at some of the stuff that we've been talking about?
All right, distortion.
Distortion. You go first.
Okay, well, you just looked at a circuit or a solution that we have for measuring distortion, where we're going to capture the entire signal. Over here, I have a sketch just to refresh everyone's memory. So the circuit under test is an inverting amplifier circuit. This is an LM358. And the device that we're going to test it with is the NI4461. And it has an analog output channel that we're going to use, and then the output of the circuit will come back in and go into an analog input that we're going to use. Now, so there's a lot of stuff in this chassis, but we're only going to use this one piece of equipment right here, the 4461. It's got BNC cables going to our circuit under test right here, and we're going to analyze it over here in software. So this is National Instruments Signal Express. This is a software environment where you can configure your hardware, you can take measurements, you can perform all kinds of analysis on the signals that you get back. So the first thing we're going to do is create a sine wave to send to our 4461. So we go ahead and say create signal, and it brings up this block here. And now, as you see here, there are a variety of signals that we can create. We can create sine waves, triangle waves, square waves, but a sine wave is good for what we're going to do today. A sine wave is a repeated signal, which means we want it to just put it in the buffer one time and just output the same wave over and over.
So this could also be an arbitrary generator?
So it can also be arbitrary, or at least you can choose from several different functions, and you can create your own custom waveforms, and there is a way for you to send those out as well. So we're going to adjust the amplitude of that to 3 volts, and I'm happy with the rest of those settings. So I'm going to go ahead and go up here and close this out. Now, we haven't really done anything with the hardware yet. We've just created a signal in software. So let's go ahead and send this guy out. We're going to say generate. And so now we're sending this, and if you look down here, we're sending this to our PXI 4461. The rest of these settings I'm happy with, so I'm going to go ahead and close that as well. And at this point, I can go ahead and click this continuous run button. And you can't see anything yet, but what's happening is that sine wave has been loaded into the PXI 4461, and it's being sent out and sent to our signal under test.
It's going there already.
It's going there already.
Wiggling.
So what we want to know, we want to look at it. So let's go ahead and we'll drop down another block here. And this time, instead of create signal or generate signal, we're going to go to acquire signal. And
the other half of the card.
The other
acquisition
half. And here we go. It's up and it's already live. And sure enough, there's our
Jumping
sine
all
wave.
over there.
It's jumping all over the place.
I don't suppose you could trigger that. That'd be hard to do. wouldn't it?
It's very difficult, but not in Signal Express.
Click, look at that.
So
Gorgeous.
we've got it locked in there. The rest of these settings I'm happy with. And so there's our 3-volt sine wave. And one of the really nice features about Signal Express is displaying things. So we had that little window open, and that was nice. But what's really cool is I can click this and just drag it right on over to this graph here, and it just shows up, auto scales, perfect. Now, so far, what this looks like is a pretty fancy oscilloscope run through a computer. But what I'm about to show you are some really cool tricks that you can't always do with an oscilloscope, but what you can always do with Signal Express. So I'm going to right-click on this guy and on the signal, and I'm going to say send to our distortion block. So that just pops this guy up, and right away we have live data, and you can see that there is a, I'm going to go ahead and stop auto scaling so it doesn't jump around so much.
So the bottom is an FFT.
So the bottom is an FFT. You can see that we've got a fundamental right here at 1 kilohertz, right where we set it up.
Yeah, 3 volts.
And it's about 3 volts. You can't really tell because this is in dB, so it's difficult to tell the scaling. But if you look up here at the top, you can see the time domain version of the signal and tell that that's 3 volts. And if you look down here to the right, you can see that the THD is about 0.2%. So that's not that good, but we're going to have a way to improve that.
It is a 30-year-old part,
It is
right,
a
Bob?
30-year-old part.
And it wasn't meant to have good crossover. Now, earlier you had this thing hooked up just reading itself, just a loop back, and you did the same distortion to show us how low the distortion. What was that distortion?
It was 1 millipercent.
Yes, it was 0.001-ish%. It was a little under that.
Yeah, that's why the signal generator is of such quality. It's not really affecting this memeasurement.
No, this measurement is
It's
well
so
within,
far worse.
well
Okay.
within the capabilities of the
this is a
4461.
24-bit, 200 kilobit a sample.
24-bit, 200
Wow.
kilosample per second.
So it's better than CD.
It's actually 204.8. It's meant for
Oh,
audio
sorry.
applications.
I'm sorry.
So we have
Cheated you a little.
that for you.
God forbid I should round off.
So we're going to go ahead and close this. And the next thing I want to do is drag this spectrum over here to the graph. Now what's going to happen if I try to put a spectrum and a sine wave on the same graph?
Time domain, frequency domain.
It's going to make two
Or
graphs.
destruction.
Ah, smart. Wow.
Very smart.
Okay.
And again,
It's still doing the auto scaling,
it's
right?
jumping
That's just
around.
trying to help
we'll
us.
We'll just turn that off.
Quit helping.
So now you can see our signal. Now we're going to get even trickier. So these are some things that you can't do with an O-scope, at least not quite in this way. So with this distortion signal, I'm going to open this block back up, and there's a little tab here that says export signals. Right now we're exporting the input signal. So in other words, it's sort of a pass-through mode for software. But instead of pass-through, let's on the way through, we're going to remove the fundamental. So we're going to remove the 1 kilohertz tone right here. So as soon as I select this, that 1 kilohertz tone has disappeared. Now you'll notice up at the top, what we have left, we used to have a sine wave here, but we no longer have a sine wave. Now we have what's left when you take the sine wave away, which is just your distortion.
So now you've emulated the old analog
So now
distortion meter with the notch filter.
We've emulated the analog distortion meter with a notch filter. Yeah,
Oh,
with,
that's what I'm going to do too.
that's
Same
what-
idea.
That's
Okay.
it's the same idea that you're going to do.
And
This
so this is time domain here. That's showing you
Time
where
domain.
the distortion's happening in the sine wave. And this is your frequency domain with the main spur subtracted.
That's right. Yeah, that's right. Signal Express makes this very
This
very
is
easy to do.
beautiful.
So let's close that now. I know you're already pretty excited about it, but I'm going to show you some even more cool things that you can do, because remember, with our analog example, you can tell where your distortion is coming from. One of our goals is to be able to look at the signal, or to look at the distortion signal, and to be able to do something useful with it. I mean, right now we can look at it, but we can't do anything useful yet. We want something useful to do with it. So I will. That exported time signal, which is just our distortion signal, I'm going to go ahead and send that to a block where I'm going to multiply it up. So I am going to multiply our distortion by 20. Now, that's real easy to do in Signal Express. So I've multiplied the distortion, And now our distortion, if you look at this signal here, our distortion is now a volt. So I think we're going to be able to see that even on the scale of the input signal, which is 3 volts. So, so let me close that. And so we have our exported, or our scaled signal.
Just dragging it
Just
onto
drag
the
it
screen
on
like
over,
before.
there it
now
is.
It makes a third for you.
And the next thing we're going to do is take that scaled signal and we're going to add it back in to the original signal. So we're taking our amplified distortion, we add it to the original signal that we had. Just come over here and we can select which 2 signals we want to add. Any of the signals we've looked at above, or any signal that's present in this environment is fair game for us to look at. So the scaled signal, we want that one. And here, any of these signals that are present, we can look at. So we're gonna. This is that raw input signal, and we add those 2 together. If you look up here, you can see what the sum looks like. And I'm gonna go ahead and close this. And this resulting signal, I'm gonna drag over.
Drag it on like you've been doing.
And actually, I'm gonna drag it up to this top one. So now we can see, overlaid on top of each other, the input signal, and then the input signal sum with the distortion signal. Now, we'd like to get a little bit better of a look at that, so I'm going to go ahead and turn the X scaling, auto scaling off, and change this to 2 milliseconds. And the other thing I'm going to do is thicken this up just a little bit, so you guys behind the camera can see that signal. Let's make it even a little bit thicker than that. So
this is great. This is like
So there we have the input signal with the distortion multiplied big enough that you can now tell that it's crossover distortion.
Yeah, that's not really
real
what's
time.
coming out of the part.
So this is real time, so if I make it bump its head.
So you've run it into the rail. You can see the white waveform is run into the rail. That's the actual
That's
signal.
real time.
That's real
And
time
then there's
data.
your distortion product. Boy, that's gorgeous.
And
And of course, you can soar it. You can take pictures of it. You can email it across the world. All that happens
automatically. You could automate email generation
Oh,
across.
this is sweet.
So
Well, how do we get rid of that distortion?
how do we get rid of the distortion? That's right, with the magic 10K resistor. So what I'm going to do is I'm going to put a 10 kilo ohm load on this circuit right here.
So this is loading the output. So
This is loading the
takes
output.
the AB output stage and kind of makes it a Class A.
That's pretty clean.
Oh,
There we go.
gorgeous!
10K
Look at
to
that.
V minus.
10K
Nice
to
trick.
minus VCC, and the distortion is
Minus
all
100
but-
and 110 dB roughly.
yeah. So we've
Just with
done
the
a lot
10K
with
resistor.
done a lot
yeah.
with a 10K resistor.
On a 30-year-old part.
And a
that's
30-year-old
good.
part.
Now the LMV 358,
Can
right?
we put our camera on this thing? LMV358.
That's
this
the
is a
new
new
part.
improved version
For low voltages.
for low voltages that does this without a pull down, so it does
Yeah,
probably the
most-
same kind of distortion.
Yeah, rail-to-rail output.
Yeah,
So
90% of the op amps made now don't have this problem because
This
they
is-
were. The LM324 was
Not only
never
our-
really designed.
Not only our worst high distortion product, it's everybody's worst
Yeah.
high
Yeah.
distortion.
It's, yeah,
But it was meant to
it's
be a
not
low-cost-
just national semiconductors part that does this.
Right.
All the
Yeah.
it's the
LM324s
architecture
do
of
it.
these low-cost old Jelly Bean op amps.
Yep.
And
It's just the way it was done.
That's how we got the cost targets back 20, 30 years
Oh,
ago
it's
to
just,
make
it
a
wasn't designed.
20-cent part. Okay, well that's great.
Very good.
That is great stuff. Now, Bob, are you going to
Now-
show us some?
I can show some views in the crossplot mode. I'm a very lazy crossplot guy. I could put this thing in real time, but I'm much too lazy. This thing is running what? A kilohertz? Below a kilohertz. And
Real time meaning show the actual sine waves?
I can show sine waves.
Okay, right.
But this simply shows that the semi-point error is quite small. It's sub-millivolt, and I can change the AC cancellation of the gain. I can get it down to almost nothing,
So you're
and then I can turn up the frequency, and I can turn it down again.
So you're nulling out the phase change?
I'm nulling out the phase, which is basically the gain bandwidth product term of an op
You
amp.
change the frequency, there's a different,
So
the
this is the
delay is
one
the
with-
same, phase changes.
Yep, 21K, 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 21K. You subtract the input from the output, and I can adjust the frequency characteristics. So now up at, 2 kilohertz, 8 kilohertz, it still has extremely low error, and there's no distortion. If it was distortion, you would see it because it's directly added into the output. So this is another way of doing something similar to that. We get high resolution by adding and subtracting in the voltage domain, in the analog domain, and we don't have to do much subtracting in the digital domain, but we can then digitize this signal if we need to. So if we need to do subtraction at 60 megahertz, this is capable to do it because all we have to have is resistors and capacitors. So this is another alternate way of getting similar results. I like this one better, but that looks like fun too.
It's good stuff. Now, everybody's probably asking, they see how cool this stuff is. It's like, what's it cost? $100,000, $200,000? Because it is a full, real NIST quality. We could take published data sheet information because it's NIST quality instruments.
No, if you're in the next 10 callers, no. Basically, this is the chassis and the controller and the PXI 4461, which are the only things we're using out of this today, probably get for around $10,000.
Yeah, less than
thereabouts. And in addition to that, I mean, don't forget that this is throwing in a free computer. I mean, this is a fully functioning computer. It has an Ethernet port. It has a GPIB port, so there's a lot built in.
Yeah, so instead of a box this big,
instead of a box that big,
and you could hang storage on it.
Wintel PC.
Right.
That's right. That's right. Standard. This is Windows XP running. So.
And so what's the pretty red and black thing? What's that?
That's these are some of our other products. This is
Right.
the NI 4070. It's a 6.5-digit flex DMM. What that allows you to do is something you can't really do with a normal DMM. Which is it'll export the raw ADC data, which actually runs at 1.8 megahertz.
So it's a precision.
It's a precision digitizer.
Yeah.
That's a good way to look
So
at
rather
it.
than have some software person decide how to hook the dots up, you can look at the raw data.
You can look at the raw
and
data.
see trends and little flickers.
That's
that
right.
help you.
It lets you use a DMM and have high resolution, high DC stability, but at the same time you can look at waveforms and kind of get an idea of what the data looks like. Because a lot of times, whenever you just have a normal DMM, you have a little digital display there, and there's some numbers flickering, and you can't make heads or tails of that. You can't really tell what's going on. But with this product, you can. You can graph it out. You can even look at higher frequency things. It's great for looking at power supply noise.
That's like a 7-digit DMM.
And it's like a 7-digit DMM. Now, when you're running at 1.8 megasamples per second, you don't have 7 digits of resolution.
Physics is physics.
Physics is physics.
But that's replacing a box maybe this big.
But that's replacing a box.
So now you've taken the computer box. You still got all this. You want a nice big monitor. Modern days, you don't want to work on a screen that big like you'd have to on a big dollar test equipment. Instead, you got this. This box goes away, the computer box goes away, and then there's more. There's what, 3 or 4 more other instruments?
That's right. We also have a a DIO, digital I/O board here with a 100 megahertz digital I/O product. We have a 14-bit 100 megahertz, 100 megasamples per second digitizer. We also have a 100 megasamples per second arbitrary waveform generator. So you can do a lot. We might not be able to talk Bob into getting rid of his analog scope, but you can do quite a bit with this 14-bit 100 megasamples per second digitizer.
And certainly with the you could do Crossplot if you want to do
Crossplot.
Right?
You can do yes.
All that flexibility is there.
You have it's like a scope that you'd have on your desktop. It's just that you have access to the raw data, and a lot of times the measurement you want to do, if it's not built in to that box that you have, a lot of times those measurements, let's say in FFT, you might have a scope box where the FFT is not built in. That's okay. In Signal Express, you can just drag that to the FFT block and it does it for you. So you have access to the raw data.
That's good stuff. I like it when you talk about you could just bring it on carry-on luggage and put it on the overhead
That's
compartment.
Right. Yeah,
an entire test bench worth of stuff.
We got a few strange looks flying out here putting that in the overhead bin, but nobody gave us too hard of a time.
You're just logging the data for the flight, right? If you had to, you could.
It's a little white box.
Yeah, this is beautiful stuff. Anything else, Bob?
I can't think of much else. I think you've covered your stuff. I've covered my stuff. We didn't look at as many amplifiers as we wanted, but we covered several. And I think we're in good shape. Well, thanks very much.
Thank you.
Thanks very much, Paul. Friends, thank you.
Okay, thanks a lot.
Thank you for coming to Bob Pease' webcast about distortion and stuff. Hope to see you pretty soon.